Hi, welcome to my poster. At the top of the mantle transition zone, Olivine transforms to Wadsleyite at around 410 km steps under equilibrium conditions. In this ambient mantle, the Olivine-Wadsleyite transformation conducts with a nucleation and growth mechanism, which involves thermally activated atomic diffusion. And the subsequent wave speed increase upon this transformation leads to the discovery of the photon discontinuity as a global feature, thanks to seismology. In contrast, lower temperatures inhibit such diffusive processes. Therefore, we are curious about how Olivine transforms to Wadsleyite under lower temperature, and how does the corresponding photon discontinuity behave inside the subducting slab. This is our research region, the Kuril portion of the Western Pacific subduction zone. To more effectively sample the structure inside the slab, we particularly choose seismic repasses along the depth contour of the slab in this NN prime direction. And we will notice that in cross-section NN prime, the slab seems to be flat, especially compared with another cross-section which is along the down deep direction. In this NN prime cross-section, almost all the seismic repasses are traveling inside the slab. This will make smaller features in the slab observable due to a natural stacking effect. We note that the tomography results in these two figures are from one of the most recent full waveform inversion model FWE18. And we just use this tomography model to calculate its corresponding synthetic waveforms, the blue ones, and compare that with the real data at 8 seconds. I think that the waveform comparison is roughly pretty well. However, if we go to higher frequency at 2 seconds, obvious mismatch occur between the black data and the blue synthetics from the model FWE18, which indicates that even for the most recent tomography model, it is still a smoothed version of what's really going on Earth. And our goal is to modify this model in this certain cross-section to fit the high frequency data. In practice, we keep the regions outside of this dashed box unchanged and only change the model inside this box. By adding an extra 1D perturbation to the previous model. We prefer to only add in a 1D perturbation. This is because we want to fit the data with the least modification to the current model to avoid introducing unnecessary structures. And the results show that by simply adding in a 1D perturbation, the new synthetics, the red one, can fit almost every wiggle in the black data. Let's look at the inverted models. It's surprising that there is a low wave speed zone around 400 kilometers. And if we refer to the N prime cross-section, we will notice that actually around 400 kilometers, it is inside the slab. Which means inside the slab, there exists a low wave speed zone, which is even smaller than the speed of the ambient mantle. We note that this is only one model that can fit the data. To search for all the acceptable models, we performed 500,000 simulations and found that trade-offs between the p-wave speed reduction and the layer thickness do exist. For example, for this model, the wave speed reduction is around -20%, and the layer thickness is about 15 kilometers. If we double the wave speed reduction to 40% and halve the layer thickness down to 7 or 8 kilometers, with this model, it can also fit data. These trade-offs are due to the resolution of the seismic waves we are using. Specifically, at 2 seconds, the final zone of the P wave is about 20 kilometers. But from all the accepted models, we will know that the P wave speed reduction ranges from -20% to -90%. It is still, even for the -20%, this value, it is still an extremely low value. Interpretations. During the Olivine-Wadsleyite transformation in the cold slab, the nucleation and growth mechanism is inhibited. Instead, another diffusionless transformation with shell mechanism might occur, and an intermediate phase, epsilon phase, should transiently exist in condition of limited diffusions. The theoretical model has been proposed almost 2 decades ago, and theoretical calculations show that the shell modulus of this epsilon phase is even smaller than Olivine, which yields to a smaller p-wave speed than the ambient mantle. However, this theoretical model remains to be only a hypothesis until very recently. In 2017, the first sample of this intermediate phase has been observed or discovered in sharp meteorites, which finally confirms the existence of this intermediate phase. And the dramatic p-wave speed reduction we have found might provide the first seismic evidence for the possible existence of this epsilon phase on our Earth. Nevertheless, any phase transformations necessarily induce long-lived grain size reduction, which is also known to reduce p-wave speed. Whichever phase transformation, we propose that the extremely low wave speed reduction we have found should correspond to a layer of partially transformed materials, possibly a mixture of Olivine-Wadsleyite and this new epsilon phase. And if this epsilon phase do exist on Earth, the new transformation pathway it provides will significantly enhance the transformation from Olivine to Wadsleyite in the subducting lithosphere. Thank you.